Okay, so in this video we're going to examine the rank of a matrix, but before we do that, to motivate the idea of the rank of a matrix, let's firstly look at the problem of linear equations. Okay, so let's say we have the setup where we have a11 x1 plus a12 x2 plus a13 x3 all the way down to a1n xn is equal to b1, and then we go all the way down with these linear equations. We go to m1 x1 plus am2 x2 plus all the way along to plus mn xn is equal to bm. So basically we have m equations in n variables, and we could represent this by a matrix. We could represent it by the matrix a11, a12 all the way along to a1n down to am1, am2 all the way along to amn. Okay, and we could multiply that by the vector x1, x2 all the way along to xn, and say that that is needs to be equal to this vector b1 all the way down to bm. Okay, so when you view it like that, let me just, oh dear, we're going on to the back of this piece of paper. So when you view it like that, when you view it as a matrix acting on a vector x, and we're saying that it's equal to b, then what the problem becomes is saying that we're acting this matrix, this matrix is acting on x, and we want the solution to be equal to b, and we are asking, are there any such vectors? Is there a vector x which has these components, let's say x1, it's actually a column vector of course, so x1, x2 all the way down to xn. Is there such a vector where if you plug it in like this, you'll get b out? So, one way of viewing what we're doing is to say that we have these, if you redraw out this matrix A, then it is A11 all the way along to A1n, and then all the way down to AM1, which goes all the way along to AMN, okay? So we have this, this matrix like this, multiplied by some vector x1, x2, all the way down to xn, and we're saying that it is needs to be equal to this vector b1 all the way down to bm. Okay, and one way of viewing what we're doing here is that we could have a11 all the way down to am1. Basically, what these linear equations correspond to, what multiplying this by this vector corresponds to, is multiplying this vector by x1 plus the next vector along, a12 all the way down to am2 multiplied by x2 plus all the way along to a1n all the way down to amn, and multiplying that by xn and saying that that needs to be equal to b1 to bn. And so that is what if you think about this, this is that system of linear equations we had originally, because we're saying, okay, each one of these components, when we add up all of these vectors, each of the components has to agree. So b1 has to be equal to a11 times x1 plus a12 times x2 plus all the way along to a1n times xn. So here we do have this system of linear equations. So this is one way of viewing what we have. And when will a solution be possible? It will be possible when this vector here is in the span of these vectors here. So recall that the span of a set of vectors, so let's say of the set of vectors a11 all the way down to am1, and then a12 all the way down to am2, and then all the way along to a1n all the way down to amn, that set, the span of that is a set of vectors itself. It's a vector space. It's the set of all vectors of the form, let's say, what can we call the coefficients? Let's say c1, a11 all the way down to am1, plus c2 times a12 all the way down to am2, plus all the way along to cn of a1n, all the way down to amn, and the conditions on this is that it's a bit on a slant here. The conditions is that ci's are all elements of the real numbers. So that is the span of these vectors, basically. So it's all linear combinations of them, and this forms a vector space because you can add any two vectors here, and you will get another vector here, and you can multiply them all by a scalar, and again you'll get another vector of this form. Simply because if you add any two, then it just corresponds to adding the coefficients, and when you add two coefficients, you'll get another element of the real numbers. And similarly, you can multiply any element here by the real numbers, and it will just correspond to multiplying all the coefficients by that real number, which will give you another real number, i.e. another element of this set here. And you can check if you want all the axioms of vector spaces, you know, so that it forms an abelian group under addition, and that scalar multiplication distributes over addition, and things like that. But they do all hold. So this is a vector space, and basically this system of linear equations will have a solution if b1 to bm is an element of this span. So it's an element of this set here, which we'll just call, let's say, S, the spanning space. This spanning space becomes very, very important to whether this system of equations has a solution. And I just want to emphasize that the number of variables you have and the number of equations you have, n and m, we're not assuming that they are equal at the moment, not at all. Okay, so the theory of rank then, the rank of a matrix, the rank of a matrix. So let's say the matrix A11 all the way along to A1n, all the way down to AM1, all the way along to AMN. The rank of this matrix, which we usually denote as little r, is equal to the dimension. R is equal to the dimension of the spanning space. So basically, every matrix you can split it up into these column vectors here. So here we took all of the column vectors here, and we worked out this spanning space, and the dimension of that spanning space is the rank of the matrix. Now, a theory from linear algebra, which I have no intention of proving, because I don't know how to prove it, but a theory from linear algebra is that if you take the spanning space of the row vectors, i.e. you take the span of this set instead, A11 all the way along to A1n, and then it goes on to AM1 all the way along to AMN, then the span of that is also equal to the span of the span of the column space. Okay, so this space here, generated by the column vectors, has a special name. It's called the column space. And this space generated by the row vectors is called the row space. So this is the span of the row space. Well, it's the span of these vectors is the row space, I should say. The span is the row space, and it's again all linear combinations of these where the coefficients are real numbers. And a theory from linear algebra is that the dimension of the row space and the dimension of the column space are the same. So dimension of row space is equal to dimension of column space. And this constant associated with any matrix is called the rank of the matrix. And it's given this little symbol r. Now, let us go to n by n matrices, because here the case is very special. So let's say we have an n by n matrix. So let's say m is an element of mn over the real numbers, over the field of real numbers. So we're now dealing with a very specific case. Then, if we look at the system of linear equations, let's say ax is equal to b, then we can take the rank of the matrix A, which is the dimension of this column space, it's also equal to the dimension of the row space. Then this equation is guaranteed to have a solution. Guaranteed to have a solution. Providing what? Providing that the dimension of the column space which is the rank of the matrix, is equal to n. Guaranteed to have a solution if this is the case. So it's guaranteed to have a solution if this is the case. So really what I should have is if this is the case, it implies that you have a solution. And the reason is that if the dimension of the column space is equal to n, then that means that basically the column space is equal to the whole vector space, is equal to Rn. So yes, you're using a different basis for your Rn. You're using the basis which is your column vectors, the column vectors of this matrix A. But, so for instance, let's take a matrix, for instance, I want to give you a solid example. So if I take a matrix up, if I take a vector up here, let's call this 1, 1, 1, and then I take a vector down going this way, and then a vector going, let me just get some that are definitely going to span. So let me just take this vector here, which is 0 in the x direction, minus 1 in the y direction, and 0 up in that direction. We've got 1, 1, 1. So that, if we take all linear combinations of that will span a plane, because any linear combination of a single vector is going to be a line, and then if you add every possible combination of this one here, then you'll get a plane of points. So we need a vector that points off up in this direction here. So I think if we took the vector, let's say, what should we have? Let's have minus 1 in the x direction, 0 in the y direction, and 1 up in the z direction. I hope that those are linearly independent, meaning that this one cannot be got in terms of these two. I cannot write this one as some multiple of this one plus some multiple of this one. This one was not in this plane. So when I take this plane and I add every possible linear scalar multiple of this, I will get every possible point in the entire three-dimensional plane. So if I take this vector, it would be 1, 1. If I take this matrix rather, it would be 1, 1, 1, 0, negative 1, 0, negative 1, 0, 1. So by taking by taking different linear combinations of this, so let's say x1, x2, x3, where these are real numbers, I can get any vector on the plane. So if you give me any vector in any vector in the free space, so if you give me any vector in free space, b1, b2, b3, then there will exist some linear combination of these vectors such that this is equal to this. So you are guaranteed to have a solution to the system of linear equations if it is true that the rank of the matrix is equal to n. What about if the rank of the matrix is not equal to n? Then we have more difficulty. That means that the spanning space is not equal to the whole space. So you are not guaranteed a solution. So not guaranteed a solution. Guaranteed a solution. But still, you have at least one vector in here. You have at least one... so for instance, let me give you an example. Let me give you... let's draw another picture. Let's take the vector, a really simple one, 1, 0, 0. And then let's take the vector 2, 0, 0, and then let's take the vector 3, 0, 0, drawn a bit out of proportion, and let's put all of those into a vector. Let's have 1, 0, 0, 2, 0, 0, 3, 0, 0. Now if I take all linear possible combinations of those, well, these are not linearly independent because this one is 2 times this one, and this one is 3 times this one. So by taking all linear combinations of 1, 0, 0, I will get this line here, taking all scalar multiples of it. But that's the same thing as I'll get by taking all linear combinations of 2, 0, 0. And when I add them together, I will still only ever get a vector on this line. So adding these two vectors doesn't make your sample space, doesn't make your, not sample space, I'm thinking probability, doesn't make your vector space, it doesn't make your vector space any bigger, your spanning space any bigger. So what about if I want a solution to this equation? x3, and I pick this, I want this vector, I want you to find me some linear combination of these vectors which is going to equal 0, 1, 0. You won't be able to do it. There is no solution to that. On the other hand, if I pick a vector such as 1, 0, 0, there are absolutely loads of ways you can pick x1, x2, x3. You don't just have to pick, you could make x1 equal to 1, and you could have 0 of the other two. So take one of these, make 0 of the others. But you could have 1 of the 2's, and then minus 1 of the 1's. That's another solution. In fact, there are infinitely many solutions otherwise. So, infinitely many solutions, if you happen to pick a b vector which is in the spanning space of these column vectors. Infinitely many solutions if b happens to be in the columns, be in the spanning space, happens to be in the space spanned by the column vectors, which is the column space, in the column space. Okay, so that's a quite nice way of viewing when we have, well, it's a quite nice geometrical interpretation of when a system of linear equations has solutions. And it turns out that if this is the case, if the column vectors do not span the overall space, i.e. the rank of the matrix, if the rank of the matrix A is less than n, and of course we know that the rank of the matrix, as you can see here, the rank of the matrix must be greater than or equal to 1, because you most definitely have n vectors here, and in the very worst case, which is what I've given you here, all of them are linearly independent, but the spanning space that they span will still at least have dimension 1, because if you just have one vector, it will have spanning space 1. If you add in loads of others that are linearly dependent, yes, it won't make it any bigger, but it won't make it any smaller either. So the rank of the matrix is most definitely greater than or equal to 1, but if it's less than n, then it implies that the determinant of A is equal to 0. So that's a way of telling whether the column vectors are linearly dependent, i.e. one of the column vectors can be written as the linear combination of the others. Okay, and this useful theorem that I told you earlier, that the column space and the row space have the same dimension, tells you that if you have some column vectors which are linearly dependent, then the row vectors of the matrix will also be linearly dependent.